Hi, my name is Drew Griffiths, and this is my presentation for Physics 2212, Lab 1, Charged Tapes. So the purpose of this lab is to observe the interactions between two pieces of charged tapes and figure out the magnitude of the charge of one piece of tape. We must also find out what fraction of atoms gave up electrons. And the materials I used in this lab were clear tape, a ruler, and two boxes. And the two fundamental physical principles I used in this lab were first Coulomb's law to calculate the electric fields, and then also the gravitational force equation because this lab was based near the surface of Earth. So you can use Newton's second law that F equals ma, and A in this case is the gravitational constant. And the results for this lab were that we calculated the charge on each tape to be 1.81 times 10 to the negative 8th coulombs, and the number of electrons lost by each piece of tape were 1.13 times 10 to the 11th electrons. And here are initial conditions for the lab. The mass of each piece of tape was 0.00021 kilograms. The tape length was 0.21 meters. Tape width was 0.0190 meters. The atom length is 1 times 10 to the negative 10th meters. And the distance between the two tapes were 3.8 centimeters. And for the first part of our experiment, we placed one tape on the table, and then another tape was placed on top of it, and we ripped it off, creating a charged tape on the one we ripped off. This tape was attracted to our hands when we brought them close, so we knew it was charged. And we then rubbed a pen with cloth, which made it a negative charge and brought it close to the tape. And we were observing whether the pen attracted or repelled the tape. And it attracted, so we determined that the tape had a positive charge because the pen we knew was negatively charged. And for the second part of our experiment, we used two charged tapes. We put one piece of tape on top of two boxes and then held a second piece of charged tape underneath it. And we determined that the tape on top was floating and it had zero momentum. So that meant that there was zero net force in the y direction, meaning that the electric force and the gravitational force had the same magnitude in this case, meaning there's zero net force. And here is my code for this lab. At the top, I listed all of my initial conditions, such as the constant using the Coulomb's equation, and then the charge of the electrons in the tape. And then again, the mass of the tape length, tape width, gravitational constant. And then here in the second part, calculated the gravitational force using the equation I showed earlier, and then I solved the Coulomb's force equation, rearranged that to solve for Q, and then printed that out and made the model. So some discussion points for this lab is there were some sources of error in the lab, and that is because the charges of the tape were likely not the same, and that when we handled the tape, it likely changed the charge. And then the assumptions we made in this lab were that we treated each piece of tape as a point charge, which is obviously not because it's a full piece of tape and not just one individual point like we treated it as. And we also ignored air resistance and other outside forces such as like the circulation of air in the room that would affect the y component of the. And then two discussion questions for this lab. What if electrons and protons charges were flipped? And the observations we made in this lab would remain the same because the charges would still be the same and therefore repel, because the electrons both repel each other. Even if those are both positive charges, they would still repel each other and the tapes would repel. And then why is it important to handle the charged tapes as little as possible? Because the charge will begin to neutralize itself when contacting neutral objects such as my hand, and we want the tapes to stay charged for the purpose of the experiment. And then the conclusion for this lab that many objects can become charged easily when interacting with everyday objects. Electric forces are everywhere in our everyday lives, and again, Newton's laws apply to almost everything.